For this next problem, we're going to look at completing the square as an intermediate step to being able to actually integrate this type of problem. Now, completing the square can be used as a technique to get an integrand into a point where you can actually integrate it. And in this particular case, we're going to kind of use it as a precursor to integration. So let's go ahead and look at the integral of 1 over the square root of x squared plus x. Now you would look at this problem and you think it looks pretty straightforward and pretty basic, but I can't use a u substitution here. I could factor out an x and actually a radical x, but that's not going to really get me any further either. So all of our basic techniques that we have won't work. You could try integration by parts, you might get that to work, but this one will fit with a nice trig sub after we do completing the square. So let's go ahead and look at completing the square here. Now with completing the square, the first thing that I need to remember is the linear coefficient, this leading coefficient, needs to be a 1, and it is in this case. So let's look at this. We have x squared plus x. The leading coefficient is 1. Now what I do is I take half this linear term. Well, the coefficient here is an implied 1, and half of an implied 1 is a 1/2. 1/2 squared is a 1/4. But I can't just add a fourth, I also have to subtract a fourth to keep this as basically adding 0. And then what I do is I factor each piece. So I'm left with x plus, and remember half my linear term, half of 1 was 1/2, quantity squared minus 1/4, which is 1/2 quantity squared. Now if you FOIL this out, you will get x squared plus x plus a fourth. And then we're writing this separate here because if I combine these, I'll just get back to my original problem. So this is my completing the square. This is what I'm going to put in underneath that radical. And if you look ahead, this is of the form u squared minus a squared. So that's kind of giving us an indication now that a trig sub would be a nice solution to this problem. Underneath the radical, in place of x squared plus x, I'm going to write x plus 1/2 quantity squared minus 1/2 quantity squared, and of course I need to recall that I have that dx around here as well. Now we want to make a substitution of some sort. It looks like in this particular case I have a u squared minus a squared form. When you have a u squared minus a squared form, the recommended substitution is to let u equal a secant theta. So we need to identify our u. U in this case is x plus 1/2. It's just not a variable, it's actually the binomial x plus 1/2. And a in this case is 1/2. So making our substitution, I get u, which is x plus 1/2, is equal to a, which is 1/2, secant theta. Solving for x, I'd subtract the 1/2 across, and I'd get negative 1/2 plus 1/2 secant theta. dx then would be the derivative of a negative 1/2. The derivative of a constant is 0. Dragging along this 1/2, the derivative of secant theta is secant theta tangent theta d theta. Now as the name trig sub suggests, let's go ahead and substitute back into our original problem to see if we can get something that I can integrate. And at first it's not going to be pretty. It's not going to be anything that's simple to integrate. But after I simplify with my algebra skills, then it'll get a lot better. So substituting in, let's go ahead and look underneath this radical first. X plus 1/2 is equal to 1/2 secant theta, and of course that's quantity squared. So this is 1/2 secant theta quantity squared minus 1/2 quantity squared. Now commonly we forget this, so dx is equal to 1/2 secant theta tangent theta d theta. I see a couple obvious things to do here. For instance, this 1/2, let's go ahead and pull it out front. So I have a 1/2 out front. Now underneath this radical, I have a 1/2 quantity squared, which of course is going to be a 1/4 secant squared theta minus 1/2 quantity squared is a 1/4. And of course we need to drag along this numerator. Now you can already see that the 1/4 is common in that denominator, so let's go ahead and rewrite that as well. 1/2 is out front. I'm going to factor out a root 1/4 from my denominator. When I do that, I'm left with secant squared of theta minus 1, and hopefully this kind of looks a little bit familiar. This is a Pythagorean identity. Now here, continuing to simplify further, I have the square root of 1/4. Okay, the 1/2 I'm dragging along from up here. The square root of 1/4 is 1/2, but we're dividing by 1/2, so in effect we're multiplying by 2. So that 2 pops up top here. Now, secant squared minus 1. We have 1 plus tangent squared is secant squared. So if I subtract the 1 across, I get tangent squared is equal to secant squared minus 1. So this denominator becomes the square root of tangent squared of theta d theta. And of course we need to write along secant theta, tangent theta. The square root here, sorry, the 2's cancel. The square root here, the square root of tangent squared is just tangent. The numerator I'm left with secant theta, tangent theta, d theta. And lo and behold, the tangents cancel. So now I have the beautiful simple integral of secant theta d theta. Well, the integral of secant theta d theta is not one that we know. It's not a nice antiderivative from a Calc 1 type of derivative, but it's one we're going to have to use quite a lot. So I suggest that you memorize it and keep it in mind. I'll provide it to you on tests and quizzes. The integral of secant theta is going to be the natural log absolute value of secant theta plus tangent theta. Okay, now we have this integral done, and again, you want to memorize this one. We're going to use it a lot. I will provide on tests and quizzes though. And there's also another one that's going to show up that we use as well. The integral of cosecant seems like it would be handy to know, and I'll bring that up when we need to. Now we need to remember that we need to convert this back to x. So next step is to convert back to x. Okay, the way we convert back to x is we use our original substitution that we had. Okay, hopefully I'm picking this up again in the right spot. I kind of had a bit of a pause there, so if I'm not, I'm going to start again at this converting back to x. When we convert back to x, we need to find our original substitution, and our original substitution is when we let u equal a secant theta, and I have x plus 1/2 equals 1/2 secant theta. If we solve for secant theta here, I'd multiply both sides through by 2, and so when I multiply both sides through by 2, I get 2x plus 2 times 1/2, which is 2x plus 1 over 1. Now this doesn't really help because secant theta is not one of those nice trig functions like sine, cosine, or tangent, so you need to remember the relationship here. Secant is 1 over cosine. SOHCAHTOA, cosine is adjacent over hypotenuse, therefore secant is hypotenuse over adjacent. So we need to take this hypotenuse over adjacent idea and plug it into a right triangle. So plugging into the right triangle, I mark an angle theta. Here's my hypotenuse over adjacent. And then using Pythagorean's theorem, I can solve for this opposite leg. And when we solve here, I went ahead and simplified underneath the radicand. You can factor out a 4, and in fact, since it's underneath the radical, you have a root 4, which simplifies to 2. So in this case, I'm going to use this opposite side to be 2 root x squared plus x. Now we need to sub it back into our original solution. Our original solution was up here at natural log secant theta plus tangent theta. So subbing in, natural log of secant theta plus tangent theta. Secant theta I already solved for up here was 2x plus 1 over 1. Tangent theta, tangent is opposite over adjacent, SOHCAHTOA. So here's my opposite leg over my adjacent. And of course I can simplify from there, and this is my solution. So it's a pretty long problem, but they're also very fun to work. Now if you do this one in Maple or Wolfram Alpha, they might simplify these quite a bit differently, so you might not recognize in this exact form. Now when you look at the natural log of a plus b, you know, this 2x plus 1 plus 2 root x squared plus x, you might say, oh, the log of a sum, isn't that the product of the logs? No, 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 it's the log of a product is the sum of the logs. I'd need a natural log for both of these in order to simplify this expression. So this is simplified as far as it goes. Now again, these problems are pretty long, but the key to this is to make the correct substitution. Don't forget your dx, don't forget to sub everything in, and then once you integrate, once you get to a point where you can integrate, make sure that you convert your thetas or whatever variable you're using back to x. Thank you. Hope you enjoyed working on these problems.